Welcome to the deep dive. Today, we are strapping in for a pretty serious intellectual launch. We are tackling one of the most ambitious and influential books ever written about, well, existence itself, Stephen Hawking's A Brief History of Time.
Yeah, and this is really less of a book and more of a grand intellectual journey. Our mission today is all for you, the learner. We want to pull out the essential concepts, the deepest insights, and those moments that really just bend your perspective on reality.
So you can walk away with a real structured understanding of it all.
Exactly,
Well,
because the book's goal is just, it's monumental.
it is. I mean, it tries to explain the origin, the structure, and the ultimate fate of the entire universe to people who, don't have a PhD in physics.
Right. This isn't about memorizing equations. It's about shifting your mindset. It's about engaging with reality itself, with Hawking as your personal guide through the cosmos.
And he's asking the biggest questions, the ones humanity has wrestled with forever. Where did the universe come from? Did time actually have a beginning?
What are space and time really made of? And then he gets into the really daring stuff.
Yeah, the things that blend science and philosophy. Are there other universes? Can science explain everything? And, is there any room left for a divine creator?
But the key thing, the core invitation of the whole work, is that Hawking doesn't give you easy answers. He's not trying to.
No.
He invites you to think deeply, to question your assumptions about how everything works, and maybe most importantly, to accept that uncertainty is just built into the fabric of reality.
Okay, let's unpack this. Let's start with maybe the hardest concept for our daily lives to grasp, the flexible nature of time. We're so used to clocks just ticking forward, right? This universal constant. But Hawking just throws that idea right out.
Well, that's the radical starting point. The old Newtonian view was that time is absolute. It's the same everywhere, for everyone. But the insight from Einstein, which Hawking really runs with, is that time is not absolute.
It's woven together with space-time.
Exactly. It's a fabric. And that fabric is shaped, it's warped by what's inside of it.
So if I'm on Earth and my twin is orbiting a supermassive black hole, their clock is literally ticking slower than mine.
Much slower. It can speed up, it can slow down, all depending on gravity and motion. This isn't theory, it's observed reality.
Right.
The GPS in your phone has to account for this every second.
Wow. So the more massive the object, the deeper the dent in that space-time fabric, and the slower time passes nearby.
Right. And that idea that time is flexible is absolutely essential when we look back to the very beginning.
Which brings us to the Big Bang, this idea that everything, all matter, all energy came from a single point of infinite density.
And the key thing to remember is it wasn't an explosion in space. It was the expansion of space itself.
And we have real solid evidence for this, don't we?
Oh, absolutely. Hawking talks about two main pillars of proof. First, the simple fact that we can see galaxies rushing away from each other. The universe is expanding.
And the second one is cosmic background radiation. That sounds really technical.
It does.
Yeah.
But it's actually one of the most beautiful pieces of evidence in all of science. It's basically the echo of the Big Bang.
An echo? What do you mean by that?
Okay, so think of the early universe as this superheated, dense, opaque fog, a plasma where light was just trapped, bouncing around.
Right. You couldn't see through it.
Exactly. But then, about 380,000 years after the Big Bang, the universe cooled down enough for atoms to form. And at that exact moment, light was finally free to travel.
The fog lifted?
The fog lifted, precisely. And that ancient light from the moment the universe became transparent, it's still traveling today. It's just that the universe has expanded so much that the light waves have been stretched out into faint microwaves.
So it's this faint heat, this glow that's everywhere in the cosmos.
It's the thermal fingerprint of the universe's birth. An astonishing, direct signal that proves the universe had a beginning.
But that raises this huge philosophical question that Hawking dives right into. If there was a beginning, a time zero, what happened before that?
That's the edge. That's where physics starts to touch metaphysics, and it leads us to the force that governs it all.
Gravity.
If we connect this to the bigger picture, we have to talk about Einstein's general relativity. This is the mechanism Hawking uses.
And the key insight here is that gravity isn't some mysterious force pulling things. It's something else entirely.
It's the manifestation of space-time curvature.
Okay, let's use the classic analogy. Space-time is like a giant, stretched-out rubber sheet.
Perfect. And when you put a massive object on it, like the sun, it creates a dent, a curve.
And a smaller object like Earth isn't being pulled by the sun. It's just following the straightest possible path through that curved sheet.
The curvature tells it how to move. That's gravity. And when we look at a black hole, well, that's not just a dent. That's a puncture, an infinitely deep collapse in the fabric of reality itself.
So massive objects warp reality. The universe is flexible, not fixed. And that takes us right to Hawking's signature topic.
This is where the book becomes truly fascinating. Black holes.
They're the ultimate expression of that warped reality. A massive star dies, collapses inward, and creates a singularity, a point of infinite density.
And once you cross its boundary, the event horizon, there's no coming back.
The point of no return. You'd have to travel faster than light to escape, which is
Impossible,
yeah.
right. But then comes the really shocking insight, the breakthrough that cemented Hawking's legacy. He merged the world of the very big general relativity with the world of the very small quantum mechanics.
And came up with the idea of Hawking radiation.
Which is just radical. For decades, everyone thought black holes were eternal, cosmic vacuum cleaners that only ever got bigger. Hawking said, no, they can evaporate.
But wait, how? How can the ultimate prison, a place that even light can't escape, leak energy? That seems like a total contradiction.
It does, but it all comes down to the weirdness of the quantum world. See, in the vacuum of space, pairs of virtual particles, a particle and its antiparticle, are constantly popping into existence.
And then immediately annihilating each other.
Right. They sort of borrow energy from the vacuum for a split second. A cosmic IOU, like you said. But what if a pair appears right at the edge of a black hole's event horizon?
Uh-oh.
One particle could fall in, while the other one escapes. The one that escapes becomes a real particle carrying real energy away. And that energy has to come from somewhere.
It comes from the black hole itself.
From the black hole's mass. So very, very slowly, over unimaginable timescales, the black hole radiates energy, loses mass, and eventually evaporates.
So even the most powerful objects in the universe are not eternal. That's mind-boggling.
It really is.
Oh.
And since we just invoked the quantum world, we have to shift our focus there now, from the macro to the micro.
Okay, and here's where it gets really interesting. Because when you look at the smallest bits of reality, the universe just stops behaving in a way that makes any sense to us.
We enter the realm of the uncertainty principle.
Which basically says you can't know everything about a particle at the same time. You can't know both its exact position and its exact momentum. The more you know about one,
The less you know about the other. It's a fundamental limit on our knowledge.
is it fair to think of it like this? If I shine a light on a tiny particle to see where it is, the very act of hitting it with that light, with that energy, changes its speed and direction.
That's a great way to visualize the effect. The principle tells us that the universe has uncertainty built into its very foundation.
Yeah.
It completely shatters that old classical idea of a clockwork universe.
The idea that if you knew where every particle was, you could predict the entire future.
Right. The universe is not a deterministic machine. The book's profound lesson is that reality, at its core, is a system of probabilities.
A system of probabilities. So particles can exist in multiple potential states at once until we actually look.
Until an observation forces them to choose one, nature isn't always precise, it's statistical. And that is so counterintuitive to our everyday lives.
Because we live in a world of big objects moving at slow speeds, where cause and effect seem totally locked in.
But Hawking pulls back the curtain and shows us that reality is just far, far stranger than our intuition can handle. This quantum foam, where space-time itself is fluctuating wildly, it's a chaotic, vibrant place at its core.
Okay, so we've gone through relativistic time, warped gravity, and the unpredictable quantum world. What's the ultimate goal here? What ties all of these threads together?
What's so fascinating is that the entire book is really a prologue to one single guiding ambition in physics: the search for a theory of everything, the TOE.
The grand prize. The hope for one single unified theory that explains all the forces of nature, gravity, electromagnetism, all of it, in one elegant framework.
It's the holy grail of modern physics. It would let us describe the entire universe from a single atom to the Big Bang itself with one set of rules.
And that search brings us right back to those huge philosophical questions from the start.
Exactly. Hawking is asking, if we find it, will we finally have a complete picture? Can human reason fully map the cosmos? And if we do, does the universe become, self-contained, self-explanatory?
He poses that famous question at the end. If we find the theory of everything, would it be the ultimate triumph of human reason? That's the stake he's putting in the ground. The idea that humanity could actually hold the blueprint of creation.
And for you, the learner, that's the power of this book. Its strength is explaining these huge ideas without getting bogged down in equations.
Uh-huh.
It just expands your curiosity, your wonder.
It is important to say, though, it's not an easy read.
Hmm,
or an easy listen. It requires focus. Some bits on, say, imaginary time can be really challenging, and you might need to rewind.
for sure. But the payoff is immense. It changes how you see everything. The core takeaway, Hawking's final verdict, is that the universe is understandable, but it is never, ever simple.
You gain clarity, but that clarity just reveals more layers of mind-boggling complexity right underneath.
Hmm.
So what does this all mean for you after taking this deep dive? It's not about being able to pass a physics exam.
No, not at all. It's about transformation. It makes you a better thinker, makes you more curious, more humble about what we know, and just more thoughtful about existing at all. It's about realizing how vast and mysterious and beautiful reality is.
And to leave you with a final thought, consider this tension we've been talking about. Hawking dedicated his life to finding a theory of everything, this great unifying order, the ultimate triumph of reason.
Yet at the same time, physics has shown us the unshakable reality of the uncertainty principle. The idea that the universe is fundamentally built on probability, on chance, that perfect, precise knowledge is impossible.
So the question is this: if the ultimate quest is for complete order, but the ultimate truth is a kind of fundamental disorder, can human reason ever truly claim ultimate triumph? Or is accepting that built-in uncertainty the real, final, cosmic truth?
It's a paradox that sits right at the heart of modern physics, and it's something worth thinking about long after our deep dive ends.